Hi guys, so welcome to again to my channel. My name is Marlasa. Today I'm gonna be show you the response of the stony story building against the dynamic load. That means the modal analysis. In the previous tutorials, we have already seen the logic combinations as well as the assigning of different types of loads to the structures. If you didn't watch tutorials starting from part 1 up to part 14, you will not have a clear understanding on these tutorials and also the next tutorials. You need to watch the previous tutorials to have a full and a clear understanding on the design of a 20-story building structure. Today we'll proceed to the tutorial part number 15, which is the response of the structure against the dynamic load. That means the response of the structures, which is characterized by the drift as well as the lateral displacements. So now let's have start the today's tutorials. So first I need to analyze the structure because I have already assigned all the loads corresponding to every structures. So here in order to analyze the structure, first I need to check whether my model is free of error or not. Now to do this, let me go to the analysis menu and click the check model. So now select all the options that are going to be checked. So now click OK. So here etabs is checking this 20-story building whether it is free of error or not. If there is an error, so we need to rectify the error because the structural results which will be obtained after the analysis has to be correct. Okay, here the model has been checked. There is no warning message were generated, so we can proceed to the analysis. So to do this, just go to the analysis, and here we need to check or we need to set the load cases to be run. So we have to run all of the load cases. And here I need to tick this one because later I will be using the center of rigidity. So click this one. No, run the analysis. Now ETAPS is analyzing these theory structures based on the provided load combinations, load pattern, load cases, as well as the assigned loads. That means the gravity loads and the lateral loads. Here we have a lateral load at the basement, at the retaining wall, and we have applied a gravity load uh, on at every floors. So all those loads will be uh, analyzed by ETAPS based on the probable provided governing combinations. Okay, now here the analysis is completed. We can check the serviceability requirements of both statics and the dynamic uh, load cases. So here, so to do this, now let me check the first the static requirements of my deflections. So to do this, I need to check the serviceability requirements. That is the vertical deflection. So we need to check the vertical deflection of the structure. So the vertical deflection of the structure has to be checked with the service load. So we need to select the service load. Just so, and here I need to make it, this is UZ, because the vertical deflection has to be checked in with the service load. That means the gravity load. So now click apply. Okay, here just we can see here we can see the vertical deflection of the maximum vertical deflection and the minimum vertical deflection here at the bottom of the window. The maximum is, it is 7.4 millimeter, and the minimum is, it is 37 millimeter, which is downward. So here the maximum allowable deflection, so which is limited by the Eurocode and the Ethiopian Building Code of Standards, that is span over 250. That is the span over 250. So when we take the span over 250, so we'll get the maximum allowable vertical deflection. So to do this, can check it. Right here, that is L over 250. And this is the limiting one, which is sigma, that is the vertical deflection less or equal to this amount, this one. And here, the length, the maximum span will be, which is commonly it is around 7 meter. It is around 750, 7,000, which is 500 divided by 25. So this equals to, let me check it, calculator. This is 7,500, which is divided by 25, equals to, which is 30. So this the vertical deflection has to be less than 30 millimeter, but now it is 37. But the serviceability requirement, which is obtained from etabs, is completely different from the serviceability or the vertical deflection, which is obtained by SAFE. So later we'll check the vertical deflection using SAFE, because etabs is not that much safe in providing the design of slab as well as the vertical deflection of the slab. Anyway, here this vertical deflection is not that much higher than the R level, and if we use safe software, we'll get below 30 millimeter. We'll get below 30 millimeter. So this is the localized defect, which is obtained at elevation of 55.68. That means, let's go to here. 27 is, it is 55.68. 55.68, which is around this point here. The maximum vertical deflection is obtained at this point, because here at this point there is a more confined HCB wall, and results the much amount of gravity load, which is corresponding to the HCB wall. So that is why we are observing the maximum vertical deflection around this point, because all the rest floors are loaded with 0.3 kilonewton per meter square of HCB wall, but this toilet zone is loaded with 3 kilonewton per meter square of the hollow concrete block walls. So that is why we are observing the maximum deflection at this point. So this maximum deflection can be revised later using safe software, and we'll check later using safe software, and hopefully it will be less than 37 millimeter. Okay, so this is the vertical deflections of the slab as per the Ethiopian Building Code of Standard and the Eurocode. So when we come to the different types of analysis, that means the static and the dynamic analysis. Here, just we can say something regarding to the different types of analysis. Because here, the first kind of analysis which has to be used during the analysis of the structure it is the lateral force method analysis. So what is lateral force method analysis? So the lateral force method analysis is used to check the responses of the structures by using the by converting the gravity load to the equivalent lateral forces. So this lateral force method is a static analysis method, which is a linear static analysis method, which has to be used in a structure having and fulfilling all those requirements. That means the requirement A and requirement B. If our structure satisfies both A and B, so we can use the equivalent lateral force method of analysis. So here, if we see this one, the first option that is going to be satisfied is they have a fundamental period of vibration d1 in two main directions. That means in x and in y direction. So here suppose uh, here we have a structure here. This is y direction and this is the x direction. So the fundamental period of vibration into main direction, that means in x and in y direction, which are smaller than the flowing value. That means 4 times Tc or to 2 seconds. So now let's check it in our model, whether our structures needs the equivalent lateral force method or the response spectral analysis method. Now let's check it. So here we have already analyzed it. Now let's check the time period. So to do this, just to go to the tables here. Now analysis, the results, the modal results, and just the modal period and frequency. Here we have the 26 modes, and here the time period is around 2.61. It is around 2.61. That means here this one is it is 2.61 second. This is the actual one. The actual time period T1. So here 4 times Tc. What is Tc? Tc is the soil parameter corresponding to. Now let's check it. Here this one. We have already used type to responses spectrum. So Tc is this one. Tc, which is corresponding to class B soil it is around 0.5. So we need to take 0.5 for Tc. Just go down. Here now 4 times Tc. This means that is 0.5 times 4, which is 2 seconds. And this one is also 2 seconds. So T1 has to be less than the minimum of either of the two. That means the minimum is, unfortunately, the two values are similar. So T1 less than 2 seconds. If T1 less than 2 seconds, we can use the equivalent lateral force method of analysis. But fortunately, the actual T1 is, it is 2.61 second, which is greater than T1. So it is not recommended to use the equivalent lateral force for our structure. So instead of this, we can use the response spectral analysis. So they must, and the second option is, that is, they meet the criteria for regularity in elevation. So our structure must be regular in elevation in order to apply the equivalent lateral force method of analysis. So the two requirements are not satisfied. So it is impossible to use the equivalent lateral force method of analysis. So we need to use instead the response spectrum method of analysis in order to observe the maximum response of the structure. So here, this is, the base shear that can be calculated from the equivalent lateral force analysis. So here, FB, which is equal to SD times T1 times the total weight of the structure, that is the total mass of the structure, times lambda. So lambda is nothing but it depends on the time period and TC. So, if the fundamental time period is greater than Tc, so we need to use lambda, which is equal to 1. If the time period T1 is less than the Tc, then we need to use 0.85. So this is described here under this one. If lambda is equal to 0.85, if T1 is less than 2 times of Tc. Otherwise, we can use lambda is equal to 1. And the m is the total weight of the structure, which can be calculated by the software, by etabs. And SCD of T1 is, this is the ordinate of the design spectrum at period T1. So here our period is, it is 2.6 second. So here at this ordinate, so what is the value of SDT? So this is SDT. So this is the ordinate of the design spectrum at period T. So using this formula, we can calculate the base shear. After calculating the base shear, we can calculate the equivalent lateral force, which will be applied at every floor. That means here we come back to etabs. So just go to the display menu. So go to the display menu, story response graph here. So here we have all these are the equivalent lateral forces, which can be calculated by using the formula, which is Fi, which is equal to the base shear F base times Zi times Mi over the summation of Zi times Mi. That is, this is, here, this is F1, F2, F7, F4, F5, F6, F7, F8, F9, 10, 11, 12, 13, 14, 15, 16, and F17. So the summation of Fi must be equal to what? The ratio Fb. So if we add up all those horizontal forces, we'll get the ratio. So here we can go to considering that EQX, that is the seismic force or the equivalent lateral force which will be applied in horizontal positive x direction. So we can take the table here. So we can take so here this one. So we can copy this one and we can paste somewhere here. So here we can sum up it. So here 40, 51.487. This is the base shear. This is the base shear. So this total base shear is similar to the base shear which can be obtained by the software. Here just to do this, so we can select here the storage here, the storage here. So select the load type. That means we can select the seismic load, the seismic force which will be applied in x positive direction AQX. So here, just when I put here, then I can get the result here. That is 40, 51.48. So this value, that means this value and these values are the same. So the summation of the horizontal forces which will be applied at every floors is equals to the total base shear which will be applied at the base of the structure at this point. Okay, so this is just to correlate or to relate the base shear with the horizontal lateral force which will be applied at every floors. Okay, now the total base shear can be provided by etabs. So when we come to down now, here during the equivalent lateral force, so we can use the estimated we can use this formula to calculate the time period and for a structure which satisfies the requirements of the equivalent lateral forces. And here C1 is, it is nothing but it is 0.075 for moment resistance space concrete frame for in our case this one. And H is the height of the building in meter, that means the total height of the building. And here we can use also this alternative estimation, that means 2 times the square root of d, where d is the maximum lateral elastic displacement, meaning just come to here, that means the maximum story displacement when if we select the x positive direction. So here the maximum story displacement is, it is around, it is 74. But when we come to x negative direction, it will be much more than the positive x direction, that is 94 millimeter. So we can take this value because this is the maximum lateral displacement. So if we put 94 here, that is 2 times the square root of 94, that is T1. This is the estimated fundamental time period, where D is the lateral elastic displacement at the top of the building. So here the other is distribution of horizontal seismic force. So the horizontal seismic force, that means the base shear can be distributed at every story using this formula. That means Fi, which is equal to Fb times Si times Mi over the summation of Sej times M1. Here S it is the maximum lateral displacements of the pointers, and M is the masses of the structure. That means Mi is the masses of the floor level, and the bottom one is, it is the summation of the lateral displacements of the floors, the floor, and the masses. And we can use, instead of displacement, we can use also the respective height here. That means Fi, the horizontal force which will be applied at every floor equals to Fb, that means the total base shear, times here Zi is the height of the story where the horizontal force will be applied, times Mi, that means the total mass of the story where Fi will be applied, over the summation of the summation of the products of the story height, the story height times the masses of the floors which are located below the point where the horizontal force will be applied. That means here, suppose if this is our structure, so this is the base of our building. Here we can take this M1, this is M2, and this is M3, and this is M4. If we want to calculate F3 here, so that means F3, which is equal to Fb, that means this one, times the height, this height, which is Zi, and this one is also Z2, and this one is Z1. So Fb times M1, that is M3, over the summation of, that is Zi is, that is Z1 times M1 plus Z2 times M2 plus Z3, that is Zi, which is, this is Z3, Z3 times M3. This is the formula, and here this is F3. So we can use the similar formula for the other stories. So this is how we can distribute the base shear to every floor level. So here there is also the torsional effect. So now let's proceed to the drift calculation. So we need to check whether the drift is okay or not, as per the Ethiopian Building Code of Standard and the European Building Code of Standard. So to do this, we need to use the drift limitation formula, which is provided by the Ethiopian Building Code of Standard and the Eurocode. Here, this is drift inter-story drift limitation here. This one. So to do this, here I have already derived the spreadsheet in order to check the inter-story drift. So the drift should not exceed the maximum limit, which is provided by Eurocode or Ethiopian Building Code of Standard. Here, unless otherwise specified, the following limits shall be observed. A. For building having non-structural elements of brittle material attached to the structure, which is this is the structural connectivity of type A. This is the structural connectivity of type A. This one. So our structure is belonging to this structural connectivity. That means non-structural elements are non-structural elements of brittle materials are attached to the structure, such as the HCB wall and the aluminum materials. All those are the brittle materials which are attached to our structure. So our structure can be categorized under this option. So that is the dr, which is the interstory drift, dr times v, which is the drift limitation value, less or equal to 0.005 h. That means uh, the uh, the maximum drift should not exceed it is 1%, because v is nothing but it is the value which is provided. So v, which is equal to it is 0.5. For importance, for importance for importance class 1 and 2, and v, which is equal to 0.4 for importance class 3 and 4. So in our case, our structure is categorized under category 2. So we can take v, which is equal to 0.5. So if we substitute 0.5 here, so dr over h, that means dr over h, it has to be less or equal to 1%. 1%. And if our structure is categorized under category B, that means for building having tactile non-structural elements, we can use this formula. And for category C, that is for building having structural elements fixed in a way so as not to interfere with the structural deformation, we can use this formula. But in our case, we can use this formula. Okay, now let me show you how to calculate the inter-story drift limit value. So here just we need to take into consideration the drift limitation of this story, this 20-story building. So to do this, just now let me say something about the story drift. Here now the displacement is according to the this equation. Here the actual displacement of a point of the structural system, which is ds. ds meaning ds is this one is this is the ds which is this is the ds de, or simply which is ds value. So ds shall be calculated as a product of the behavioral factor q and the displacement of the same point, which is de. The same point, which is de, obtained by the modal response spectrum analysis. That means de times q, which is equal to the ds. So de is, ds is nothing but it is what you call it. It is dr. Let's just cancel this one. So here This one is the displacement, and DAR is the relative displacement. Here V is it is a reduction factor for the importance class 1 and 2. So here QD, which is the amplified displacements of the center of mass, which is equal to the behavioral factor, which is Q. Here the amplified displacement, which is multiplied the amplified factor, that is the displacement magnification factor, multiplied with the relative the displacement DAR, which is this one it provide, which is the DR. Here DR is nothing but it is the product of the magnification displacement factor multiplied with the relative displacements of the joint. Here this point is nothing but here this is dr is nothing but it is ds, which is dr, or in another term which is ds, which is which is ds means that is dr. So here they obtained by the modal response spectrum analysis, with which includes the torsional effect. In our case, the factor Q, which is equal to, we can use Q is equal to what? 2.4. This is the example which I've already done by the Eurocode, but we can make this value 2.4 in our case. So the displacement is the center of mass, that is Cm, are presented in table 2.5.4. So we need to use the displacement which is associated with the center of mass. So here, just to do this, go to the display menu. So here, just to go to the graph. So here we have to make this one the response spectrum load cases. That means R response spectrum, that is positive. So here, just go to here this one, and we need to copy all those values. So Ctrl C, then go to the spreadsheet. That means the response spectrum in X, that means the AQX drift, which is we need to paste it. So here the results are what? The status of the drift limit is, it is okay. Okay, because here this one is the displacements of the center of mass, and this one is the relative displacement of the center of mass, and this one is the reduction factor for the importance class 1 and 2. So we can use the importance class. We can use a reduction factor V, which is equal to 0.5 for importance class 1 and 2. That means the importance class, meaning this one for class 1 and class 2, we can use V is equal to 0.5, and we can use V is equal to, that means the reduction factor, which is equal to 0.4 for the importance class of the building 3 and 4. So having this in mind, we can use, in our case, we can use as our building is categorized under the originally building, which is category 2. So we can use the reduction factor value V, which is equal to 0.5. So here that is the behavioral factor, that means displacement magnification factor, which is equal to the behavioral factor, that means 2.4, which has already been used during the dynamic analysis. And here we have the drift, which is equal to the elastic relative displacement multiplied with the magnification, the displacement magnification factor. So this can be provided with as listed here. And also here the drift limitation over the displacement reduction factor, that is V in percent, is that is 1%, meaning here this is provided in the code. Okay, now let me show you. Here, this one. Here, there's overview, which is less than alpha h. This implies that there over h, it has to be less or equal to what? That is alpha over v, and v is 0.5, and alpha is, it is 0.005 for a category of building having a structural connectivity, which is classified under connectivity A. That means the structural members of written material connected with the structural members. So here the drift limit is, it is 1% for our building. So there over V, which is this one, and there over H, it has to be less than the coefficient of the drift limitation to the reduction factor, which is 1%. So the status is okay. Here, all those values are less than, it is 1%. And when we come to here also, the option 2, it is also okay. So this indicates that our structures is okay for drift in the direction of positive x. And when we come to the negative x direction, just come to this one. That is Rx negative. So just come to this one and copy. Then Control C and come to the spreadsheet, then paste it. So here, the drift limitation is okay. And come to again to this response spectrum in y positive direction. And here, just go to the table and copy the displacement along y direction. So here, paste it here. Now the displacement, the drift is okay in positive y direction. And also just come to the negative direction. Okay, sorry, this is the maximum displacement. Now let me come back to the maximum here, the diaphragm center of mass. So we need to take this one. Now let me come back to the response spectrum in x direction. I have already made a mistake. So we should not take the maximum displacement. We need to take the displacements of the center of mass. Okay, Control C. So just come to an x positive direction. That is this one here. The status is okay. Come back to again to the response spectrum in negative x direction. So just come to here. Then here, copy this one. Just come to here. So in negative x direction, paste it. Here the status is okay. And I can just come back to the response spectrum in y positive direction. Then copy the displacement of the center of mass along y direction. Then here in y positive direction, then paste it. Then in y negative direction. So just copy the displacements of center of mass along negative y direction. So paste it. Okay, here, as you see, the drift is okay for all directions. So this concludes that our structure is okay for drift as per the Ethiopian Building Code of Standard and the European Building Code of Standard. Okay, now so this is all about the determination and checking of drift as per the Ethiopian Building Code of Standard and the European Building Code of Standard. So if you like this video, don't forget share it to your friends so that your friends will be getting the new updates of these tutorials regarding the structural design and the structural design of steel structure as well as the building the reinforced concrete structures. And also don't forget provide me comments in my commenting box so that I can answer your questions as much as possible within a short period of time. And don't also forget press the bell icon so that you will be getting notification when I upload the next tutorials. So this is all about the today's tutorials, which is tutorial part 15. Next time I will be showing you the P delta analysis of this story building. So see you next time. Bye bye.